let us take a specific named reaction called Prelesive reaction. Prelesive. Okay. It actually deals with epoxidation. Let me give you an example. So this is a cis compound with metachloroperbenzoic acid or a simple per acid. Per acid can be given this way. See, a simple acid is represented by this RCOOH. But if the same thing is modified as this, then it becomes per acid. Okay. Now this is when we get epoxide. Oxygen gets added across the multiple bond. Got it? Just the removal of this bond. Adding oxygen from these reagents across the multiple bond to form an epoxide. So this is epoxide or oxirane. Okay. In general, the cyclic ethers are called epoxides or oxiranes. Let me give you the mechanism. Of how this epoxide is formed. Okay. Let me take this. Now, taking the per acid, in a bit convenient manner, because we have to add oxygen. Look at this. See, as and when this bond goes here, this gets connected to oxygen. This one comes here, then this one comes here. Interesting. Come on. Let us write a transition state with all the bonds that are going to get broken and those going to get formed. Look at this. This is going to get broken. Now this bond and even this bond, these are going to be formed. Then this one is going to get broken. Oxygen, we have already got a bond, and this is going to get formed. C R, a bond with oxygen, the other bond is going to get broken. Then how about this bond? Hydrogen, this is going to get broken, then a bond between these two is going to get formed. I think this is clear. Yes. This is transition. Now, this simply decomposes. You can clearly see of what is happening. Right up to this, you got your epoxy. Right. Now let us write that. Come on. This, these two, and this one is formed. This is how we get our epoxide. Along with the epoxide, as you can see, look at this area. R, this is C double bond O. No, this is C single bond O. This is C double bond O. This is, of course, the OH group. I think you got it. Now, this is actually the carboxylic acid. Simple. We have the R group with the double bond O onto this side, then O, and then H. Okay, so this is the acid. We get epoxide or oxirane in this fashion. This is a mechanism. Overall, it is interesting to remember that this oxygen, I mean the oxygen that is connected to hydrogen is what is getting added here. Even that is also important. Sometimes it is labeled, like suppose sometimes they take it as O18. So mechanism plays an important role in such a case. Okay, so this oxygen is what has come here. Come on, this is the oxygen that you got here. Remember that. Now let us go for the second step in this, that is hydroxylation. Right. Hydroxylation is nothing but, I mean, during hydroxylation, what happens is the ring opening of the epoxide is what happens when the hydroxylation is carried out. It's not hydroxylation. It has to be hydrolysis. Of course, OH minus gets added up, but epoxidation followed by hydrolysis. Let me write it this way. Okay. Now in the ring opening of epoxides, let us consider acid catalyzed ring opening of epoxides. In fact, it is of 4 types. Ring opening can be carried out in different ways: acid catalyzed, base catalyzed, with a Grignard reagent, even with lithium aluminum hydride. So there are several varieties. You can see all of them in ethers chapter. But for now, let us consider the acid catalyzed hydrolysis or acid catalyzed ring opening of the epoxide. Come on. See, this is the epoxide. Now, initially, let us consider acid. Okay, as usual. We will still be left with a pair of electron. Now hydrogen gets connected and you get a positive charge, right? Now this whole area is been closed. You cannot come from this end. You cannot attack anything from this area, right? Just leave this area and now take water molecule. See, this water molecule gets connected. I mean, attacks. It acts as a nucleophile. Look at this. The lone pair is actually been donated to a carbon atom. As and when the nucleophile attacks, this goes towards oxygen. That's it. The positive charge gets neutralized. You can clearly see that this is anti-attack, or the attack is from the backside because the ring is being closed. Okay. So now let me write that this is anti. Then come on, see, to which you got a hydroxyl group with oxygen having both its pairs of electrons. Then this, you got two things. Okay, let us consider two steps now. Water, yes. Then finally, it is this. As and when this comes here, this goes off. Of course, even for this also, you need to use water molecule. Okay, let us take it this way. It again goes off in the form of, actually here it has to be H plus water, because as we know, H plus has got no independent existence. It exists in the form of H3O plus. You have used H3O plus and now you are eliminating H3O plus. Of course, H plus. So the thing that we get here is OH, then this, these two, then of course another OH. So you got something which has got two hydroxyl groups onto the opposite side. So this is actually called a glycol with anti-configuration, anti-arrangement, anti-glycol. Okay. Right. Let me give you an example. In fact, example gives us one more interesting point, because I'm going to take something which is unsymmetrical. Look at this. This carbon, let me say that it is a less substituted, less hindered, less crowded. Right. Whereas this one is more crowded because it has two methyl groups connected. Whereas here you got only hydrogen. This one has got two bulky groups attached. So more crowded and less crowded. This will give us another very important information as far as the mechanism is concerned. Come on, let us consider H plus. As usual, let us take it this way. Now this, come on. Yes, you got this. Now this will get attacked by water. Water. Where does this water molecule attack? No doubt it is behaving as a nucleophile. But remember, in case of acid catalyzed, say this goes and attacks this particular carbon atom. Because you know, if this carbon gets a positive charge, then that would be okay, because it is supported by two plus I affecting groups. You be very careful. Plus I affecting, in fact, it is the more stable carbocation. So remember, it goes via a more stable carbocation. So this is clear. Why is it attacking the more crowded one? Because the more crowded carbon is going to give a more stable carbocation. Yes, as and when this goes towards the positive charge, you are going to get a more stable carbocation. In fact, it is supported by two plus I affecting groups. The more crowded one, or the one that has large groups connected, will always give a more stable carbocation. So that is very interesting. Now, what do we do? Come on. CH3, then this. Let us put it this way. Come on. O, H, H. Okay. A positive charge. CH2. And you got OH here. Okay. Now, of course, we can actually avoid this, but still, let us consider a water molecule again. To just take out the H plus. Yes, take it off. This goes here. This is how learn how to make mechanism. If you can make the mechanism, you will have too much advantage. O, then H, CH2, then this OH. Anti. Okay. The two hydroxyl groups are onto the opposite side. So you got anti-glycol. So in case of acid catalyzed ring opening of epoxide, remember, the more crowded is attacked. The nucleophile attacks more crowded, or more hindered, or more substituted carbon atom of the epoxy thing. Okay. Now let us go for another very interesting concept. That is ozonolysis. Even in ozonolysis also we have two varieties. Reductive ozonolysis, then oxidative ozonolysis. This is interesting. Let me give you the reaction first. With four different substituents, they may be hydrogens or they may be alkyl. First step is treating it with ozone, followed by reaction with zinc water. Instead of zinc water, you can also use dimethyl sulfide. Very simple. Just cut it here. Okay. Cut it here. And you can simply add a double bond O here, double bond O here. So it is very simple that we are replacing a C double bond C by two C double bond O groups. Right. Let me first write the products. R1 C double bond O, R2 plus R3 C double bond O, R4. So it's very simple, involves the replacement of SC double bond C bond by two C double bond O groups. Okay. So this is the overall thing that happens during ozonolysis. Okay. Then let us consider an example. Of course, very simple. Okay, I have taken something with two double bonds. No problem. It can have any number of things, any number of double bonds. Remember, just replace the double bond by two C double bond O groups. Come on. Let me consider dimethyl sulfide so that I can eliminate dimethyl sulfoxide. Now check out. Keep it as it is. Here you get a double bond O. Even on to the other side also you will have a double bond with two hydrogens here. I've taken this area first. Now, come on. This one with a double bond O here, with a double bond O here. Here we got a hydrogen. Even here also we got a hydrogen. Then this methyl. Of course, along with that we get dimethyl sulfoxide, a polar aprotic solvent. This is how you can write the product. Suppose if you are asked to write the reactant, I mean the substrate from the product, you can go this way. Come on. Remove this double bond O. Remove this double bond O. You will get your reactant. Very simple. Write them in a manner using which you can eliminate O2. Okay. I mean the two oxygens are the two double bond O groups. You'll get your C double bonds. Nothing but it is quite opposite to what you have seen. Now let us go for the mechanism of ozonolysis, which is little bit complex. Now to this alkene, a general alkene, let us add ozone, O3. Taking the formal charge concept into consideration, let me take it this way for convenience. Now, this is our ozone. Now check out the way it gets connected. See, as and when this negative charge, nothing but the lone pair, attacks, this one comes here. And then this goes to the rescue of the positive charge. That's it. Let us see what happens. See, here we get something called malozonide. R1, C, be a little more careful. Then let me put it here onto a different side so that there won't be any disturbance. O, which is still left with two lone pairs because only one lone pair is given. Then this oxygen, even this also has got two oxygens because the positive charge is anyway neutralized, has a bond with this oxygen. Even this also has got two lone pairs. Come on, a bond between these two. Then R4. Okay, this is the malozonide or primary ozonide. Okay, now this one comes here. This one goes to oxygen, just decomposing it or is breaking up. Now again, a kind of intermediate, which can be shown this way. R1, C, you got a double bond O here, happy. We got one product, but still there is something left. On to the other hand, here we got a double bond O. This is R3, then R4. But this is still, okay, let me show this thing. Still left with a positive charge and is still connected with this, which has actually got an extra electron pair, so is having a negative charge. Now, see how it actually gets rearranged. Let me show the two pairs of electrons first. Very interesting. As and when the negative thing attacks this one gets connected here, and this one comes here. Another rearrangement. This is another intermediate. Now we get this R1, C, you got R2. See, this oxygen is in the middle of the two carbon atoms now. It is connecting both the carbon atoms. Hope this is clear. This oxygen is now bridging the two carbon atoms. Okay. Yes, this one is connected to, yes, this is the oxygen that I have written now. Then there is another oxygen, I mean this one connected. It is in fact connected to this. That's it. So this is called ozonide. Okay. Now this ozonide decomposes in the presence of dimethyl sulfide. See this. We can actually remove one of the oxygens in this way. Okay. Look at what happens. This one comes here. This one comes here. And this oxygen goes to this. Okay. So that will now become dimethyl sulfoxide. CH3 taken twice, S a double bond O. Let me actually remove this. This is not authentic. Dimethyl sulfoxide is what is eliminated. And see, you got your R1 C double bond O, R2 plus R3 C double bond O, R4. You got the carbonyl compounds. Okay. Now the interesting part of this is, see, ozone gets connected to the double bonded carbon across the multiple bond. I mean, it gets connected only at the position where there is a double bond between two carbon atoms, right? So, ozonolysis is used to detect the position of unsaturation. Position of unsaturation is detected because ozone gets attached to the double or triple bond exactly at their place. The position of unsaturation can be known from this particular reaction. Okay. This is an interesting mechanism.